So I would like the organizers very much for having me around. Maybe you could tone this down a little bit. You should consider yourself really, really lucky to be here. It's just an amazing setup, and I'm kind of aware that I'm the last slot after a hard week, and I can try keep it quite light, possibly also quite short. I don't know. That's up to you. Please interrupt me. So what I wanna tell you about is sparse linear models. What are sparse linear models? How do they differ from classical models that we all have kind of learned about in our education in scientific computing? How do we do estimation with these models, and how do we do approximate Bayesian inference with these models, and how do these two different things differ from each other, and where are the strengths and weaknesses? I mean, I don't know if it's really working. Yeah. Try to just speak a bit louder. So everybody has heard about sparsity, right? It has a lot of press. Depending on where you come from, you've probably worked on sparsity along different buzzwords. So let me just list a few here. If you're an image processing person, then you know that sparsity helps you in denoising, right? And the reason why it helps you in denoising is something that we know about images now pretty well, is natural image statistics. Wavelet shrinkage, one of the really early successes of sparsity, and image coding, image compression, right? And sparsity is kind of the driving principle behind all these buzzwords. So that's, if you're from image processing, these are words that should ring a bell. If you are instead a statistician, you talk about high-dimensional statistics, then of course you are concerned about feature selection. You have so many features, you gotta really start selecting among them. You talk about L1 relaxations, you want to learn structure of a model in a fairly cheap way. And even worse, if you want to estimate covariance between variables, then you know this scales as the square of the variables. And you really do need to do some sparsity penalization there. If you are a signal processing person, then it's compressed sensing. You get really, really excited because finally you can break the Nyquist limit. You can sample below the Nyquist threshold and still it works. And you talk a lot about sparse sampling and you prove theorems. And finally, if you're an algorithms guy, if you're like convex optimization, then it's really quite amazing that you do not need interior point methods. You can get by with algorithms that work on much larger problems. Matching basis pursuit, actually this comes from signal processing, soft hard thresholding, and a million variants of the Lasso, right? So I think there's something in sparsity for all of us. And what's behind the hype? I think behind the hype is a fairly fundamental concept, actually, and that concept has to do with what we mean with simplicity, right? So everybody in science and engineering and business, they really like simple methods, but sometimes it's really quite difficult to say what simplicity actually means. So in the old days, people had one basic notion of what they mean with simplicity, and I kind of, for the purpose of this talk, let's just call this Gaussian simplicity. And that just means if you can choose among many, many elements, then choose all of them, but choose all of them a little bit. Okay, so you mix all of them together, you mix them up, and that's how you define a simplicity. Another idea is a little bit more recent, kind of the new kid in town would be sparsity. And that would say if you have a lot of things to choose from, choose as few as possible, but if you choose them, commit to them a lot. Okay? So that's sparsity, and this is just a different way of defining simplicity, and here you can just visualize that these two different principles are indeed quite different. So, I mean, it's easy to say a new principle and so on, but then you just try it on some data and it gives you really different results. They might work better for some problems, they might work worse for others. What's important is that's it's a new thing. And this is something maybe most of you have seen. This is image coding. So the idea is that you take natural images, you extract patches from them, and then you try to explain these patches as a linear combination of basis vectors, if you want. And these basis vectors altogether, they form a dictionary, right? So it's also called vector quantization, but it's specifically applied to natural image patches. And if you do this using Gaussian simplicity as the basic principle, what does that mean? That means that the linear combinations that you're allowed to mix these basis elements over, you allow all of them to be non-zero, but you kind of penalize all of them to be small. Then everybody in the room knows what the solution for the dictionary is, right? That's something that you may have learned in the second lesson about machine learning. So the solution to this problem is PCA, so that's principal components analysis. So up here you basically see what happens if you run PCA on a bunch of natural image statistics. And basically, because natural images are translation invariant, you kind of get something like a Fourier basis. So that's kind of basic frequencies along certain spatial directions, and they get higher and higher in terms of the frequency, right? So up here you have DC components and so on, and then gets more and more. What's important is that they are very non-local, very global kind of periodic structures, right? That's PCA, and now if you do exactly the same thing, you still encode the same patches, you still encode them as linear combinations, but you say now instead of being allowed to use all of them, you're only allowed to use a small number of them, but if you use one, then you use them a lot, right? So that's sparse coding. And then you learn the dictionary. That's not so simple anymore. You can just run PCA, but you can still do it. And if you do that, you get very different dictionary, right? And that's the one thing I want to point out here is that it's not the same principle. You get different dictionary. You get qualitatively and quantitatively different dictionaries, something that's very local gratings, also oriented, and people in neuroscience, they make quite a nice story out of this. But what's important is that it gives you a different solution that has different properties, right? Even though the only thing that you have changed is the notion of simplicity. How do you want to encode these patches from your dictionary? Okay. So sparsity has been used all over the place in image processing, image modeling. Has been used to model image better. I come back to that. And this, of course, once you can model something better, you can do more with it. You can do image processing, you can clean them up, you can denoise them, you can reconstruct them from undersampled measurements. And you can even start thinking about how to acquire images more efficiently and still reconstruct them well. And in computational neuroscience, people even make this into a science, right? So how does the human brain do it? Well, maybe it's using sparsity. But it's so this is engineering, and down here you have the science. Then people in combinatorial optimization realized that sparsity is actually a surprisingly simple way of solving some of their problems. And the buzzword here is relaxation. So you relax these hard problems, you make them convex, and then you prove that under certain assumptions still works. Kind of this is the figure that kind of shows you how it works. So if you want to kind of have something that has a penalization that looks a bit unpleasant, then you could maybe smooth it out, make it convex, and maybe it still gets you to the same corner of the solution space under certain assumptions, right? Then in statistics, there has been a lot of really interesting work. So there's this very, very hard problem. At least people thought it's a very hard problem, how to learn the structure of a graphical model. People have all these local optimization algorithms, and they these work fine, but nobody can characterize them well. And then suddenly people did something very simple, Meinshausen-Bühlmann, very simple idea, based on sparse reconstruction, and they proved that this actually works, right? So this is this is in some sense an instance of that up here, but to me it's actually a very surprising fact that this actually works, and you can put this on a very sound statistical basis here. So you can learn the structure of a graphical model by a sparse regression. And then I've already talked about sparse coding. This is in some sense a higher order model learning problem, because instead of just figuring out how to code these patches, you have to learn the dictionary as well. And again, people have shown that if you impose sparsity, because this fits natural image statistics better, you can also get methods that outperform PCA quite a bit. And again, you can make science out of this. So one concrete application example of sparsity would be to image reconstruction. So in medical imaging or in any kind of imaging, you are acquiring information about an image bitmap. And this information might be linear projections of the image bitmap, like in MRI, there are Fourier coefficients. Of course, you're interested in acquiring as little as possible because that's cheaper and faster. And then given this acquisition, you want to reconstruct what that bitmap has been, right? So this reconstruction is kind of the interesting problem here. And sparsity might help you to actually save on measurements and still do a good job in the reconstruction. So why is that? Because any kind of reconstruction is always a statistical problem. You combine the measurements with the prior knowledge that you have about the signal up here. If you understand the signal better, you can do a better job in the reconstruction, and you can trade off the number of measurements with how much you know about your signal. And that is what happens for images. So images are a difficult beast to describe. A lot of people spend their whole career doing that. But one thing they certainly are not, they are not Gaussian. I almost know signal out there is Gaussian because that is what a Gaussian looks like. So if you sample from a Gaussian, you get that, and I don't know whether you see a lot of this stuff out there. So you can see that this is a Gaussian because if you just walk through this bitmap and you just you record kind of your jumps, then you always see something like this. This is a random walk, right? Kind of fluffy, noisy, and this doesn't have any structure, right? That's a Gaussian. And an image doesn't look like that. If you walk through an image and you record your steps, then you see something very different. You see almost nothing happening, right? And then you jump over an edge here. You kind of change texture, and then something interesting happens, and then not much, right? So the one thing to note here is that this statistic is different from that. And if you now make an assumption that more is over on this side, even if it's on a very low level, then it's kind of convincing, then that should work better for things like reconstruction and denoising and so on. So that is why sparsity might not be a perfect statistical description of an image, but it's certainly a hell of a lot better than something like this. Okay. Sparsity is such a strong concept for images that you cannot just do simple things like, depending on denoising is not simple, but it kind of is I would still say it's a first order problem, but you can solve even these higher order problems, which means that you can make decisions about parameters that have been influencing the image acquisition and so on, even fairly complicated things. So this is a famous one, blind deconvolution. So you get something like this. You don't get any other information than this blurry image, and your job is to guess what the clean image was, and in order to do that, you have to estimate how the camera was moved during the acquisition. You have to estimate that blur kernel, right? So that's basically a parameter that's somehow encoded in this thing. If you had some isolated dots, you could read them off, but you don't. And one thing that allows you to do that is that you know that that clean image has certain statistical properties that get more and more lost the more you blur it, right? So you can kind of optimize, in some sense, for sparsity, and then say, okay, what's the most sparse kind of inverse transform that I get by shifting this convolution kernel around, right? And there's some people in the room who just do this pretty amazingly. They've got amazing results. This is a little bit older, so you can still improve on that a lot, but I think the driving principle here is sparsity. It also can be applied in medical imaging and all over the place. Whenever you need to calibrate something and you don't want to spend a lot of work on getting ground truth, then you go to methods that just use image statistics. And then you can shoot even beyond that and say, well, I mean, if I know that knowing a little bit about the statistics of my signal helps me in order to do things with less measurements, then you could even think about under this specific circumstance, how can you optimize the way in which you acquire these measurements, right? And again, knowing about your signal is kind of the glue that allows you to go from the question, I've done these measurements, which measurement should I do? That question depends exactly on the prior knowledge that you put in about your signal class. So if you put in a different prior knowledge, like a Gaussian, then you get a very different answer, right? So that would be a acquisition optimization problem here. And again, sparsity plays a key role here. So this is the outline of my presentation. First, I want to talk a little bit about how do we model sparsity in a computationally tractable way. We're still talking about things like images, so no 1 million pixels or so. You cannot just do something that's esoteric. And then how do we take these models and we do something interesting with them? For example, we do estimation, reconstruction, denoising, and then maybe beyond that, we want to know a little bit about our uncertainty. We want to do inference over them. And I want to end a little bit by contrasting these two and show you what the one is and what the other is not. So anytime if something is unclear, this is a fairly short program, please do interrupt me. I can hopefully you take something away from this. So let's see how sparse models look like. So we need to capture the low-level statistical structure of these signals. Think about images, think about neighboring pixels and how they relate with each other, right? We need to capture the sparsity and there the non-Gaussianity. So this is just a really amazing slide by an ex-MPI person, Florian Steinke. And so here you can, in one slide, you can see what the whole concept means. So over here we're in the Gaussian world. This is a two-dimensional Gaussian prior. Think about 2 pixels next to each other or something. And so this is a Gaussian, and if you measure that Gaussian along some direction, then you get another Gaussian, right? So no sparsity here. If you take instead something that is a sparsity prior, that's a Laplacian, the only difference is that there's no square here. Then this has contours like that. And suddenly, if you condition that on some data, then you go over here and then something really interesting happens. The mass that is just smeared out in a Gaussian sense, if you condition a Gaussian on a Gaussian, you get a Gaussian, right? If you condition one of these things with a Gaussian, this is a little Gaussian tube, right? It goes up like this. Then suddenly you get something where the posterior mass is shifted towards the nearest axis. Right? If you think about it, this is exactly what sparsity means. So that mass is not smeared out all over the place, but it actually just chooses the nearest axis and gets shifted towards there. It's kind of a tilt towards the next axis. So what does that mean? If you're next to this axis, you're going to switch off the variability along here. You're going to try to be sparse. Okay? So you can do this even more. You can say, well, that's not enough for me. It's still smeared out. I want to do something that's really very sparse, so you change that exponent to 0.4, and then you condition, and then you get, obviously you get what you wanted. So the posterior mass is now completely squeezed along that axis, so very sparse. But now something interesting happens. Some of the mass also lands here. Okay, and that kind of spells trouble. Okay, that kind of spells multimodality. Ooh, that's trouble, right? 2 different modes, difficult, right? Inference going to be difficult. And we're going to talk a little bit about that trade-off, yeah?
Question. I think I understand approximately what you're doing here, but how exactly do you make these plots down there? Could you write down some mass on the blackboard?
Yeah, we can call Florian, but I think the way he did it is that he just, I mean these are not necessarily normalized. You can play with the colors. The only difficulty in Bayesian inference is if you want to plot something like that is whether you want to. Oh, how did he do these plots? I think he's just multiplying two-dimensional things. So what do these 2 lines mean? I mean they just mean that there's some Gaussian that is. It's a Gaussian measurement. It says, okay, hey, you should be kind of here, but I allow you some noise. So it's kind of low here, and then it goes up. You see? So it's kind of flat along this direction. The measurement doesn't tell you anything along that direction, and it is Gaussian along that direction. It says you should be kind of in this tube.
So you have like that's the likelihood type of thing. Like
it's the likelihood.
You just take the product.
Exactly. So if you want to do this in MATLAB, you just take the product, and then you play with the colors until it looks nice. I think that's how he did it. Actually, I mean these are 2-dimensional, so I think Florian is a smart guy. So I think he even computed the normalization constant and he used it. And so that's how he did it. So that's why these colors are probably okay. And if you did another measurement, you would get very soon to something that's kind of just a dot because it's just 2 degrees of freedom. That's easy. But I think you could do this in 3D, but I think this is just tells you the whole story here. So Kevin Murphy liked this figure so much that it's in his new book. So we need to kind of, I mean, over here we're in the sparse world. That is kind of the distributions that we want to use in order to get our sparse models off the ground, right? Apart from that, they're going to look like the old stuff, but we somehow need to go and use these guys. We need to somehow replace this guy over here because it doesn't encode sparsity. Well, that's easier said than done, right? Because yes, okay, we want to get rid of the Gaussian, but everything we know about, everything we actually can do, everything we can do at large scales is completely based on the Gaussian. I don't know if you're aware of that, but everything is based on squared norms. If you go to do anything in numerical math, a squared norm, you might wonder why that is. It's because the only thing you can really do at large scales. It leads basically to linear estimation, it leads to linear algebra. We know now how important it is to use the blast and so on. If you go away from these Gaussians, then you're completely in no man's land, okay? So we somehow need to pull this off, that we say, oh, we don't like these Gaussians, at least we don't like them at certain places in our architecture, we like these guys, but at the same time we have to reduce back to this Gaussian mathematics. So we want these priors, because they describe our signals. Gaussians do not describe any signals out there. If you want to take one thing away from this whole thing, from this whole course, is that Gaussians do not describe signals. They describe noise, right? Because they're unstructured. These guys are at least a hell of a lot better describing real signals. But because they're not Gaussian, we can't really do computations with them. So what do we do? Well, here's one idea which people figured out, is that if we could manage to represent these non-Gaussians in terms of Gaussians in some clever way, then we could get the best of both worlds, right? So possibly, maybe it's possible to have a non-Gaussian over here, then some mathematical magic here, and then some Gaussian in here. And the mathematical magic is latent variables, and you can get latent variables into the game in two different ways. Well, then kind of the Bayesian way, integrate them out, or otherwise, I don't know, no, that's silly, but you can also maximize over them, okay? And this actually works, and let's just go through this. So there's two different ways in order to go from a family of Gaussians to a non-Gaussian potential that describes your statistics better, right? One of them is scale mixture, so let's look into what a scale mixture is. Scale mixture, mixture of Gaussians. Who knows mixtures of Gaussians? Okay, so I make a little bit of a bet now. I think most of you, if they talk about mixtures of Gaussians, they think about something like this, right? So what's that? That's kind of clustering, that's EM, that's the first thing you learn. Well, maybe after what is a Gaussian, then you learn what is a mixture of Gaussian. And the reason why we want to learn about things like that is because they help us with multimodal distributions. They help us with understand things like clustering. Now, they don't help us at all with sparsity because they mix over the wrong thing. So if you want to do sparsity, you have to go and do something like this. This is a Gaussian. And these are sparsity distributions. They have the same variance. And if you look now where the mass is, then you see there's lots more mass close to zero. That's where the sparsity is. But then, and that's a bit hard to see, but it's very important, there's also a lot more mass out here in the tails. The further you go out, the worse this actually gets. So where's the missing mass for the Gaussians? Kind of here, right? And in high dimensions, always kind of square root of dimension away from the middle. That's where the Gaussian has its mass. And these sparsity guys, they have their mass completely at a different place. They have it in the tails and they have it in the center. So we need to shift the scales around, not the means. Okay? So that means we should rather mix over the scales of the Gaussian than over the means. Okay? And that's what a Gaussian scale mixture is. So you have a mixture, but it's over the variance and not the mean of the Gaussian. The mean is always zero, or whatever you want to put it, but let's put it at zero. So, I mean, once you, so this is how it looks like, right? If you want to do this in MATLAB, you sample a kind of a standard Gaussian, you multiply it with some positive thing that you sample from something else, and you get a scale mixture. So what are scale mixtures? Many things you know are scale mixtures. They have actually almost all of these things that you can look up in a statistics books. Many of them are scale mixtures. Gaussian is a scale mixture. That's easy. But spike and slab is maybe the first non-trivial scale mixture where you just say, let's take two Gaussians. Let's take a narrow Gaussian, maybe sitting at a small variance here, and then let's take a very broad Gaussian. Let's add them together. Okay, and then you get a distribution that has much heavier tails than a typical Gaussian would have, at least if it was this one. So that's the first possible sparsity potentials. It's a very simple discrete mixture of two Gaussians. You can also consider continuous mixtures of Gaussians, and then you get the whole family of things that I had on the board. You get the whole power family. You can take that alpha from 0 to 2. Of course, 2 gets you back the Gaussian, and depending on what that mixing distribution is, you get all sorts of interesting things. And for 1, you get the Laplace. And then you get also things like student t, and I could continue this list, right? So depending on how you choose this mixing distributions, you get all sorts of others. There's a funny mathematical duality between the two, and you can read this up. For the Laplace, it looks like that. It's kind of an inverse gamma or something. So that is one way how you can get interesting distributions, which are in the center actually more or less just a Gaussian by mixing over the scales. A second idea is to actually maximize over the scale, and then of course you got to weight that Gaussian. So if you look at this figure, you kind of understand that idea. So suppose I want to generate that red thing, which is a Laplace. So just suppose putting Gaussian functions below it and always make it tight so that they touch. So you can actually get that red curve by just putting Gaussians below it at every scale. Depending on how high you make them, you can generate that red potential, right? And again, you can do this with a whole sorts of family of non-Gaussian distributions, even some that have a non-differentiability up there. That's really quite amazing, right? I mean, all these Gaussians are completely smooth and regular, infinitely differentiable, but if you do this game here, you can generate things that have a peak, okay? And you can also generate all sorts of other things. Quite an interesting question is what you can actually get by taking maxima over Gaussians and just scaling them, the height. In order to address this, you kind of have to look a little bit closer into how these potentials look like. So what does a sparsity potential look like? It should be positive. So you can take the log of it, and maybe it should be even. And so you can actually look at it as a function of, say, s squared. And if you do that with these Gaussians, so if you look at this log of that and then look at it as a function of s squared, well, what do I get? What kind of functions do I get? If I do this transform, I get linear functions, right? So I take this, I take the log of that, and I look at it as a function of s squared. That's a linear function with a negative slope, right? And then you can ask, well, kind of maxima of Gaussians, and in this transformation they become maxima of linear functions. So what are functions that you can write as maxima of linear functions? Convex functions, right? So the class that can be written like this can actually be characterized as potentials whose transform is a convex function. And that kind of makes sense, because if you look at something like the Gaussian being a linear function here, and you do not like the fact that the Gaussian has too much mass here, so you want to shift the mass towards 0 and you want to shift it into the tails, then you have to bend it kind of in the convex direction, right? So to cut this short, all the potentials for which I can find this maximum representation, they are characterized by a convexity property, and that's going to be important a little bit later on. So then you can ask, what's the relationship to scale mixture? So that's the second ingredient that I could use in order to get Gaussians into the sparsity world. And it's quite interesting. People have actually shown that all scale mixtures are super-Gaussian. So this is actually a more general idea. Okay, so there are potentials which you can get by maximizing over Gaussians, and you cannot get them as scale mixtures, but vice versa, you cannot. So anything that's a scale mixture, you can also find a representation like that. Okay. So any question about this? This is just a technicality to get us started in order to build these sparse models. And one idea that you should take away from here is that by introducing an additional variable in this scale variable here, I basically manage that feed, right? I get a potential that has very non-Gaussian properties. That can go all the way to student t and very, very nasty distributions, but I can represent them as a simple transform, an integral over maximum over the scale, so I can represent them with Gaussian distributions, right? And then some of you might already think, oh, okay, that looks like a latent variable model. Maybe I can use Gaussian algebra in order to drive anything that I want, and that's exactly the right idea. Okay. So, and then you can take this idea, you can do more with it. You can, for example, so people made a lot of progress on group sparsity, but if you look at it in that way, then it's actually something that's very simple. Basically, you say, well, you know, now I don't like the fact that my potential is sitting on one coefficient. I want to penalize a whole group of coefficients to be small together, right? Either they can be large together or small together. How do I do that? Well, if I write it that way, then it's pretty easy to see that if this is sitting on the absolute value only, right, then I can just replace that whole absolute value by a norm. So I can just plug in a norm here. And then I still get a maximum over Gaussian, right? So this is still a Gaussian because a squared norm over here is just a multivariate Gaussian with a shared scale parameter. Okay, so basically you just go from univariate Gaussians to multivariate Gaussians that are where the variables are scaled together. And so there's really nothing very new in here of going from normal sparsity to group sparsity, and that is also why these algorithms look so similar, is because they just are based on exactly the same idea. You introduce a scale, which in this case is just shared among a group of coefficients, and that scale controls whether things are switched off together or are allowed to basically be large. And this is very useful. People are doing a lot with this. You can do this on groups that you predefine. You can do this on trees. You've heard this earlier on and so on. It's all this idea that you can just put some structure in here and then do your penalization on the groups. This is called L1, L2 norms, group lasso, and so on, right? So one other thing that I want to point out that's sometimes a little bit confusing is that what do we actually mean with sparsity? Okay, with sparsity, to most of us, it just means that things are either zero or they're non-zero. So that would be a sparse signal over here. So all these guys are zero, some of them are non-zero. That is not actually what you get if you sample from any of these potentials that I showed you, right? With a possible exception of the spike and slab. If you sample from any of these potentials, you rather get something like that. So that's a super-gaussian statistics, and people, you could call this soft sparsity, heavy-tailed, power law decay. There are all sorts of words for that. But what is important here is that basically none of these coefficients is exactly zero. If you sample from something that has a density, then you're not going to see a zero. If you look closer and closer, you're going to see something that goes away from zero at some point. But you're going to get something that's mostly close to zero, and then some things are much further away from zero than you would ever get if you sample from a Gaussian. Okay? So this is a exactly sparse signal, I would say, while this you could rather call a soft, sparse, or super-Gaussian signal, right? And it's really quite important to keep this apart, and it becomes really confusing. I hope that's the other thing that you can take away from this tutorial, is that where do things actually come up that look like that? Okay, and why do they come up? And I think I will get that point across, right? Because this is something people always confuse. We are actually using distributions that if we sample from then gives us something like that. So why do we at some point get something like that? Okay. But for now, it's just really important to keep in mind that why do we call it sparse? I mean, would you prefer super-Gaussian linear model? It's a bit long. But the other point is just wait a second and you will see, we will clear this up. Okay. But in some sense, sparsity is a bit of a misnomer, right? It's basically to almost anybody, sparse would mean that. But statistically speaking, it actually means that. And that is quite important if we go and do inference with these things. Yes? You can always do post-processing. I'm just wondering, so statistically, you would want to do the basic things that you do in statistics is like go from a prior to a posterior by conditioning on some data. And then you ask yourself, what do these posterior look like? And a posterior that would essentially represent a signal like that would really have to concentrate its mass on the zeros. Now, if you do this whole game of Bayesian inference with potentials like that, that is not going to happen. Okay, it's not going to concentrate mass on zeros. Well, that's just because if you sample from the prior, you get something like that, and no likelihood in the world can change that. Okay. If you do want to have exact zeros, you have to put that into your prior already. And there are some, I'm not going to get into this, but there are technical reasons why people don't do this, right? So some people do, but they, and this is called spike and slab, and you can ask me offline why not everybody's doing that. Actually, it would be actually quite nice, but it's computationally a problem. So where are we? So we've learned a little bit, I hope, about sparse models, and if anything's unclear, now is the time to ask before we move on. So maybe the most important thing that I cannot stress enough is that real-world signals are not Gaussian, okay? And people have sunk a lot of money by making assumptions that they are Gaussian. I don't know, formula that brought down Wall Street, all of this business. That is just the fact that signals are not Gaussian, or you might think about AD converters and why do we waste all our money and so on. But it's just because real-world signals are not Gaussian. And if that point gets across together with the fact that we have some alternatives today in order to make computational progress on non-Gaussian signals, you could save a lot of money, right? And I think that's what's happening right now. So there's amazing potential for cost savings by making a very simple observations. Real-world signals are not Gaussian, so you got to change the statistical assumptions that assume that they are Gaussian, and you got to sort of make that first step towards something that's still tractable, but non-Gaussian. Super-gaussian distributions are a really nice contender for that first step because they offer you a trade-off between a little bit more realistic signal assumptions and computational tractability. And the reason why is because you can represent them in terms of Gaussians. Okay, that's exactly why it's going on. And how do you do that? Well, possibly using latent Gaussian representations. We've looked at scale mixtures. We've looked at super-gaussian potentials. That's pretty much it. I think there's not much more that you want to do. And on these ingredients, you can play the game. Then there are group potentials, and just beware that sparsity means different things to different people. So sometimes it basically means super-gaussianity, which is not the same as being exactly equal to 0 on most coefficients. Okay? So then let's move on and look at first kind of applications of this idea. So sparse estimation. Let's look at the reconstruction problem. So what's the basic problem of image reconstruction? Well, we kind of want to push the limits so we don't acquire complete information. So we actually do on purpose acquire less information that we would need in order to identify what that underlying image was. Anyway, there's going to be measurement noise and so on, so probably we would even not get a unique answer if we acquired enough, but we are under time pressure, so we are not going to acquire that image completely. We are going to leave out a lot of information, say in Fourier space. And so then you have to face that basic problem that if you have an unidentifiable problem, you have to decide somehow what you're doing, right? And then the basic answer from statisticians is to say, well, you know something about the statistics of what you expect, just add that to what you've acquired, create an estimator that in some sense contains a mixture of both of these informations. That's kind of the hard facts. And this is kind of what we believe these signals to be. And then you can make a decision. And one particularly interesting way of doing that is just, it's called map estimation. And you're basically constructing a likelihood that encodes the hard facts, right? Not just about what you've acquired, but also what kind of you think your noise has been and what kind of peculiarities you think your measurement device has. Okay, I have to go into Fourier space, so my likelihood should contain a Fourier transform or so on. And that is this thing here, right? So these are the observations. This is the latent image. And then you multiply that with an image prior, and that's where these super-gaussian potentials go in. Multiply these two things, and then you maximize the whole thing. So if you multiply a likelihood with a prior, then you get a posterior, and so you're looking for the mode of that posterior. That's called map estimation. And that is basically one of the simple sparse estimators. So just to give you an idea how these models look like, that would be an image model, sparse linear image model. For reconstruction, this is the likelihood. That's where all your measurements are. That's kind of the design matrix of your measurement that tells you which projections you've measured. Here's the noise level. That's Gaussian. That's okay. I mean, Gaussian noise is a fairly good assumption for something like MRI up to some point. But as I already stressed, right, a Gaussian assumption wouldn't be quite right here. So we actually put a non-Gaussian here. We put a Laplacian here. And it's sitting on certain transforms of the image, like usually simple filters that you can apply fairly rapidly, like derivatives, like, remember running through this image and always checking what steps you did. These are just simple image derivatives. And maybe something more fancy like wavelets, okay? Important thing is that you can compute these things rapidly. And then you can look at the posterior and see what you can do with that. And in map estimation, that's what you do. If you take the negative log, it looks a little bit simpler. And then, of course, because there's a negative, you minimize that. So that's the Gaussian. So here you see the least squares part. So y minus xu, and then the noise variance there. And then here you see the negative log prior, right? So that is a quadratic function, right? So minimizing a quadratic function is something that we've all know how to do that. But here, we should not expect a quadratic function because only a Gaussian would get us quadratic function. We should expect something else, right? So if we choose a sparsity prior here, then we will get a sparse solution. And now I do mean sparsity. I don't mean super-gaussianity. If I choose something which, technically speaking, the negative log is a concave function in the absolute value, then I will get a truly sparse signal as the solution of this optimization problem. Okay, that's not so hard to show. So if we're on that side over here, where the negative log of these things is all concave in the absolute value, then you do create sparsity. You get zeros, exactly, in the mode of this posterior. And that's kind of what we want out of it. At the same time, we might be concerned about things like that. So that looks kind of bad, like multimodal, right? So how do we know if we landed here, but we actually want to be there, right? So if we're concerned with that, we should probably enforce something like log concavity of the sparsity potentials, which basically just means that the log of that is concave. If you look up here, that simply means that the whole thing over here is convex. Convex plus convex gives me a convex optimization problem. So that might be another desirable thing about the whole setup. So if you want to have a convex optimization problem, then you need to be over on this side. Okay, so you couldn't take a Gaussian, then we all know it's a quadratic optimization problem. It's the most fundamental optimization problem that you can ever solve is that leads to the normal equations. And that really goes back to Gauss, right? Or you can take also something like the Laplace, and that's still kind of on the boundary. If you want to have a convex, sparse optimization problem, then you're pretty much stuck with the Laplace potential. Okay? And the Laplace potential gives rise to what people call the Lasso, at least in statistics. So if you do want to do map estimation in a convex way, you're pretty much focused on the Lasso. And people have used this a lot. I just want to show you one algorithm for solving the Lasso, so you get an idea how these things look like. There are these kind of classes of algorithms. They are called operator splitting methods, and people have come up with many, many variants of these algorithms. It's still ongoing. And what I show you is a particularly simple one that works actually really well for image reconstruction. If Steve Boyd would be here, this is the one algorithm that he's all over the place about since the last 2 years. And it's just because this thing works really, really well for many problems. So let's just go through this. Suppose you want to solve this problem here. So what's the difficulty about solving this problem? Well, I think the difficulty is that there's two things that come together. If one of them would not be there, it would be easy. So two things come together. One of them being that, well, that is not quadratic, so if it was quadratic, I could just solve it with it's the least squares problem. I solved the so-called normal equations. It's a linear equation system, and there's tons of software for solving it. So this is not quadratic. It's actually L1, so it means it's the sum of absolute values, okay? So the other problem that I have is that there's coupling here. So there is a non-diagonal linear transform here that takes me from, say, the image to the measurements. There's coupling, so the pixels are coupled through multiplying with this x. So the observations do not sit directly on the pixels. If they would sit directly on the pixels, then this thing would decompose as an independent sum for each pixel. This thing anyway decomposes, if you think about this B being identity, and then I could also solve it. Okay, so the reason why this is hard to solve is because there's coupling here and there's non-Gaussianity here. And I need to decouple these things, right? That's a good algorithm, has to decouple these things iteratively, and that's what this algorithm is doing. So if I want to decouple these two terms, maybe I should start by calling this different names. I just call this U and I call this S. And then I just say, hey, but at the end, at least I want to have equality here, right? Yes?
Could you just say again what B is?
So B is this. So it's just I mean, you just if you want to just understand that algorithm, think about B being the identity. In image processing, real world, we cannot use the identity because an image is not sparse. The pixels are not sparse, but certain transformations that you do on the pixels are sparse, like the derivatives. That's why the B is there. If you only want to understand the algorithm, think about B being the identity. Okay, because it really doesn't matter that much. People call it the sparsity transform, simple local thing. Okay, and of course you can do also all sorts of optimization on that one. This thing you cannot do much about. Okay, you cannot say, oh, I'm going to choose that to be the identity, because that wouldn't quite fit your MR measurements, right? But here I have some considerable freedom, so think about it being the identity. So first part is I say, okay, I'm going to rewrite this a little bit. I didn't change the problem, but I kind of put the complexity over here. Because why? Because now if I would want to only solve this problem over here and this constraint wouldn't be there, it would be rather easy, right? I would just solve it independently and I would be done. So now I have to somehow do something about this equality constraint. So what kind of techniques do you know to deal with equality constraints? So there's a fairly general thing you can do, which I think you will know if you studied. Yeah, exactly. So you would dualize it. Okay, you would create a function that becomes large if it's violated. So that's a dual. So you invent a Lagrange multiplier and you add this thing here. And then you're facing a saddle point problem, right? So people actually in this algorithm, they do something more. They add something fairly harmless, I think, but which makes a big difference. They add this smoothing term, which kind of is harmless, at least at the end, because at the end this should be 0, so you just add 0, right? But doing the algorithm actually makes a big difference. So now they go from a Lagrangian to an augmented Lagrangian, and that is kind of makes the algorithm work better. So now that's the problem you have to solve. You have to minimize over U and S, you have to maximize over B, right? It looks like a big mess. The original problem was here, and you made it only much harder by introducing new variables and new terms. But actually, it turns out that by doing so, you've decoupled the problem. And now you can actually afford to solve independently for U, independently for S, and then do an update for B, and actually get somewhere. You can even prove convergence. Okay, and that's the amazing thing. You add new things, you add complexity, and that is actually not a bad idea because it decouples the problem. And now look at what happens. So now actually if you, so now you see why people add this term, because now they can pull these two things together and they get one quadratic term. You can look at the slides later on, it's like really simple. And then you get a method that people call the alternating direction method of multipliers, and it's a very simple way of solving this problem. It's just really a round-robin optimization over the different variables. So you optimize over U. That's interesting because now you only have quadratic terms because this doesn't depend on U. So that's your least squares problem. You can solve that. Then you have to solve for S. That is one of these problems that actually looks kind of hard, but it is simple because this is decoupling. There's no matrix here anymore, right? So now this is just the sum of one-dimensional things, and you can write down the solution. Okay, if all our Lasso problems had diagonal measurement matrices, then we would be done, right? In some sense, denoising is that, but okay. And then you can do a Lagrangian update, and then you iterate that, and you can prove convergence of this. It's a little bit tricky. You got to pick that lambda in the right way, but I don't think it's a big deal. There are harder things in practice. And this works really well. Let me just show you how this works for MRI reconstruction, where it's particularly attractive. So for MR reconstruction, you have this problem that you have the measurement matrix is, so what do you measure in MR? You basically look into Fourier space and then you record straight lines in Fourier space. Okay, so you go from image space into Fourier space, so that would be a discrete Fourier transform. And then you have this pattern, so this basically this J pattern here, which says, hey, record these guys in the middle, but you can maybe leave out some of the higher frequencies. And this is what this index is here. What is important here is that this is a discrete Fourier transform, it's an orthonormal transform, which we can apply really fairly rapidly. And then you also have this sparsity transform, which, if it's not the identity, is still something pretty simple. It's made of either wavelet coefficients very often, and they are orthonormal, or otherwise they are very simple finite impulse response filters, like derivatives, first, second, and so on. Okay, some people even learn these filters, and they gain some more power out of that, right? But they are really careful that these things remain finite element response filters. And why is that? Because the reconstruction algorithm can make use of that. So the only point in that algorithm that is actually tricky, right? Everything else would not even depend on the model. The only point that's tricky is the least squares part, okay? And the least squares part is basically the problem where you have to solve for u, and it leads to this equation. You have to solve this system of equations, right? It's a big system of equations. This is as big as the image is, so that can be easily 1,000,000 pixels. You got to solve this. Of course, you do not want to compute that matrix, but here's how you solve it. So this is the Fourier transform, and here are my sparsity. So one thing I could do, I could plug in this in here, right? And then you can see that, well, maybe I can pull these Fourier transforms outside, right? So let's do that. So now I get a diagonal matrix here. It's just kind of something that selects pixels. And then I get also this filter. So here I have the filter in the middle, right? And then I get Fourier transform. So what happens if I apply the Fourier transform to some finite element response filters? They diagonalize in Fourier space, okay? They have a diagonal spectrum. So that is also a diagonal matrix. So this whole thing is nothing else but the Wiener filter, right? So it's diagonal, so I get a very easy problem to solve as part of this algorithm, right? I only have to run, instead of have to solve a linear system with some complicated algorithm, I get a direct solution in terms of 2 fast Fourier transforms. So I get an algorithm that per iteration needs only 2 FFTs, okay? And it doesn't need many iterations, so if you look at some simple problem, but it still goes, it still shows you that sparsity makes sense. So this would be an undersampled reconstruction here. And then you see, well, if you do this and this many FFTs, you get, here you have still a pretty noisy solution, and then the sparsity cleans it up. And very quickly you converge, and that's it, right? And each of these iterations costs you only 2 FFTs. So this has really been quite influential nowadays in MRI, and the reason is because you do really get better images, and you get them at a constant factor more than the solutions that you had before, right? So really, and using the same kind of technology. So if you have some hardware that it can speed up linear reconstruction with Gaussian penalization, you can possibly iterate a little bit over that, and you get the new thing. Okay. Any questions about the sparse reconstruction? Yeah.
So do you include positivity on the image, or?
I could do that instead of sparsity, positivity, and I could do both of it. It's not so clear whether it's in MRI. It's not so clear what the numbers mean. So you can But in other modalities, you probably want to encode non-negativity as well, and the same mechanics would actually apply. I mean, you would have to do a little bit more work because obviously that's not symmetric potential anymore, so you cannot do these transformations anymore that I was showing, but it's kind of in the same ballpark. You add a few constraints, linear constraints, and you can still do it. Okay? But in this case, we don't have any non-negativity here. Okay. So what's the message here? I think the message is that I think I kind of, the promise that I had was to say, well, you know, you can go create estimators that are there's the time-honored, you know, the normal equations that everybody's using since Gauss to solve everything out there in the real world. Normal equations, right? And now you can go from this point and say, okay, if I do want to have a better estimator, why is that better? Because it encodes the signal statistics in a better way. Then I can do that, and I can actually reduce the computational problem of finding the solution of this estimator to the old problem, okay, by using algorithms like the one that I had up there, or other algorithms. You can also use older algorithms like iteratively reweighted least squares. And the main message is that you can have this best of both worlds. Okay, it's just a constant factor away from what you had before. And you do not even have to change your methodology. You can use your FFTs, you can use your conjugate gradients and so on, right? It's just a loop around it if you want. And some thinking about what the right model is, because it's easy to say something is Gaussian. If you go away from that, you have to say, what is it? Is it not Gaussian, but is it student T? Is it Laplace? What's the computational consequences of that, right? One thing you should take away here is that one computational consequence is, for map estimation, is that if you do want to have exact sparsity, you do have to look at the fact that the negative log of the sparsity potential has to be concave as a function of the absolute value. What that means is you have to be beyond the Laplace. The Laplace is linear if you look at it in that way. Okay, and anything, so the Laplace is linear. Why? Because on one side, you only have to look on one side. So this is linear, right? Anything that goes, so this is the Gaussian that's convex. That doesn't really help, doesn't give you sparsity. And then you can go beyond and get something like this. And that gives you even more sparsity. But the Laplace is kind of the edge case. That's already concave and it gives you sparsity. If you want to have stronger sparsity, you go and make it concave. But on the other hand, you might be interested in convexity, because then you just run it once and you don't have to restart, and that is a nice feature, and it's also something that algorithmically is easier understood. And then you have to be careful that the negative log is convex in SI. Okay, so now you're talking about this thing here being a convex function, and this, of course, not being a convex function, not even on one side. Right? So if you want to have sparsity and convexity, then you are, in terms of map estimation, you are poised to use the Laplace. And that is exactly why there are so many more papers about people using the Laplace, so the L1, than anything else out there. Okay, because it's this trade-off between convexity and sparsity. But there's also good reason to go beyond it, because for some problems the Laplace is just not strong enough. And then you might want to go beyond, and maybe I have some comments about that at the very end, that it's actually perfectly possible to go beyond. And then maybe another very important message here is that you do not have to run interior point black box methods. This is like one of the most successful parts of really dirt cheap, simple convex optimization methods called first order methods that, you know, theory people wouldn't look at them. But in applications, they just beat everything else because they're so simple. Everything, you know, if you can do an iteration with 2 FFTs instead of solving a crazy quadratic programming problem in every iteration, then of course you're going to do that, and you're going to see maybe it converges fast enough for my problem to the accuracy that I need, right? And for image reconstruction, that just means, well, if the pixels don't change anymore, then who cares about further gains in accuracy, right? If you can't see it anymore, then it's fine. Good. Any questions still about this estimation? So everybody understands where the sparsity comes from. So it doesn't necessarily come from actually the statistics. It only comes from the fact that the mode of that posterior happens to have sparsity, right? If I sampled from that posterior, and we're going to get to that, then I would not see zeros. It's just the mode. Okay. So now I want to talk a little bit about Bayesian inference with these models. Okay, so now we are going to go beyond estimation. We are not going to output a single point. We are going to be concerned about a distribution now that in some sense characterizes the solution up to the uncertainty that we should have in it, right? We did not sample that image completely, so there has to be remaining uncertainty, and we are going to represent that just like everybody else in statistics with a distribution, right? That distribution might have a mode that might be the solution to the Lasso, but we care about the distribution now. Okay. So why do you want to do that? Well, one thing, it sounds a little bit weird to say that I haven't really acquired enough information about that image, but still I'm just going to output a single solution to the practitioner, right? Obvious question is, well, you know, how you should be uncertain in that decision. So where are you more uncertain? Are you maybe more uncertain here or there or something? I mean, do you think that this pixel is more certain than that pixel? So it's really a little bit of a weird idea just to output one image, right? In particular, as you know, that if you would change a little bit of that information, you would flip around a few of these things, you would get a different image down here, right? You want to understand about the fluctuation that across the different answers that you could actually give, right? What is the fluctuation across all these different possibilities, right? So instead, what we could do is we could just somehow give back an ensemble of solutions, right? And this, in some sense, is what the Bayesian posterior is. And if you now want to use all of these solutions, well, that just go ahead and use all of them. And the basic idea is to integrate over them instead of just to maximize over them. So that would be the difference between inference and estimation, and you should really be careful because some people call everything inference, including estimation. For the purpose of this talk, I'm going to call inference something that outputs a distribution or that outputs samples of a distribution and does not just estimate a single point. That would be estimation. Okay, but sometimes people call everything inference that gives you some answer to a statistical problem. So one reason is maybe you want to output some uncertainty, but there are reasons beyond why you will want to do inference. In some sense, you can just do more with inference if you manage to pull it off. And here's, for example, let's go back to these examples so you can calibrate your model. So suppose your model now has additional parameters. It just doesn't only have the latent image. It also has parameters like, for example, in blind deconvolution, you might be interested in the blur kernel. In multi-frame super resolution, you might be interested in what the camera positions were and how, you know, in which orientation the camera had. Maybe the point spread function. In image coding, that was kind of this patch coding, you would be interested in what the codebook should be. And then you might want to learn the whole prior. You might want to learn what the sparsity transform is. You might want to learn what these potentials are. And you might want to learn what the filters are that you apply to the image. Right? And you might learn a whole sorts of different things. And so now suppose that your problem is not so much reconstructing that image, it's learning what these parameters should be, right? And the important thing is that the only thing that you allow yourself for this problem is the raw data. You do not have to have tuples between clean image, noisy image, clean image, blurred image. You only have the blurred image, right? And that is, I mean, you could call it unsupervised learning, but in the context of computer vision, I think it's just a pain in the neck to calibrate anything. If we had methods that could be calibration free, it would be just so much nicer, right? So if you do have a control of Bayesian inference, you can do this. At least you can apply, you know, something like maximum likelihood to it. So that would be like this, right? So now you need to maximize the likelihood of the parameters, and the likelihood function depends on the observations, but only the ones that you know, so only the raw data. Think about the blurred image. So you need to look at the likelihood of the blur kernel given the blurred image, right? What do you do with a clean image? it's not known. So if you don't know something in a distribution, you've got to integrate it out. So that's what you have to do. You have to look at the likelihood, the prior, integrate over the image, right? Then you get the marginal likelihood, and that's what you maximize in order to calibrate your model, right? This is maximum likelihood estimation, and it accounts for the uncertainty in the image, and it accounts for what parameters do I have, what degree of uncertainty in the image, right? So then you can also say, well, I don't really like to do this integral. I want to do max, and this is actually what most people would do if they do like map estimation. So they would maximize over the image, plug that in, say, okay, that is my best guess for what that image is. Of course, that guess depends on the parameter. Different blur kernel, you get a different guess, right? You plug that in, and then you kind of outside also maximize over the hyperparameter, okay? That sometimes works, but often it doesn't, and it's kind of pretty clear to bash it if it doesn't work, and it's pretty clear to explain why it doesn't work, because it basically just ignores the uncertainty in that it just plugs in the best guess, and that's a very non-robust way of doing things. If it doesn't work for you, still want to do it, then two advices are basically to pick a problem where this parameter is much smaller than that one, like for example the image coding problem, the dictionary learning problem, or otherwise to apply additional engineering. Okay, but you could also sort of just invest a little bit in how to get approximate inference going, right? And then you could also try to optimize acquisition by doing something like sequential experiment design. The idea here would be it's very natural if you had a distribution over the image, given the measurements that you have done already, then you could ask for what the next best measurement is just by looking at that distribution and check out in which direction you are most uncertain about things, right? And then you align your next measurement with that direction, and that's how you can find a very informed way of optimizing your acquisition. And it's something that completely depends on the fact that you understand which parts of that image you have not measured very well right now. So that would be another motivation. So let's just see how possible algorithms could look like that could get approximate inference going. I'm only going to talk about variational inference. There's another whole big class of techniques that are called Markov chain Monte Carlo. You can use them as well. They have strengths and weaknesses, and I just don't have that much time, so I'm just going to talk about a class of methods that is a little bit closer to map estimation than Markov chain Monte Carlo, and these are the variational methods. They're basically pretty much the same as an estimation method, except that what you're trying to optimize over is not a point, but it's a distribution over points. So the problem of integration is intractable, so you cannot integrate over a million pixels or something. That's just not possible unless the distribution is something that basically it's a Gaussian, then you can do it. But if it's not, then you cannot do this integral. So what do? Well, it's the same idea as the sparsity potential. You reduce it back to Gaussian. You say, well, if I can integrate something like that, if whatever is below the integrand is a Gaussian, then why not approximate whatever is below here with a Gaussian and then do the integral and then see how I can use this idea in order to make it into a well-founded principle. So let's approximate the non-Gaussian posterior by a Gaussian, which would then allow us to do the integrals. Okay, again, we are using the Gaussian in order to get off the ground. And so now you only have to kind of figure out how to do this. And there are many ways how to do it. I only want to show a single one. Maybe this is one of the most simple ones. But the basic principle that links all these methods is that they target this normalization constant here. So you look at this, right? Here's the likelihood, here's the prior, and here's this normalization constant. That normalization constant is the marginal likelihood. The log of that is, I could just call it the master function, and this is the function that you want to approximate. It's the moment generating function of the posterior. It encodes the information in the posterior. And all the variational methods are going after that one. So what glues all these variational methods together is they try to approximate or bound this log partition function. Okay? That's not an easy thing to do because obviously I can compute it. It's exactly the solution to the whole problem, but it's a good target to actually think about. And people spend a lot of effort to kind of chip away at this log partition function and get, in some sense, a good approximation or bound to it. And I'm going to give you one example how to do that. And in order to understand that one example, we have to go back to the super-gaussianity, okay? And we have to really understand what it means. So, so remember how that was. We have certain convexity property that allows us to call something super-gaussian. And then we can show that we can represent that potential as a maximum of Gaussian functions. So why is that? Let's just quickly go into why we can represent these potentials as maximums of Gaussians. And the reason for that is I'm going to use the convexity property now. I'm going to say, okay, if that transformation of that function is convex, then we all know that, and that's a basic principle of convex functions, is that you can represent a convex function as the maximum of all its lower bounds, right? So now you can do the following. You can say, okay, that's my convex function here. And I can put a lower bound wherever I want, right? Say I put it here, and I get that tangent here, right? And you can now even create a duality out of this by basically taking that point where you lower bounded it, and then you say, okay, well, what's the slope of this lower bound? Well, it's 0. And then you say, oh, what's the offset of that lower bound? It's something like minus 0.37. And then you can say, okay, well, the slope was 0, so I'm going to 0, and I go at minus the offset, so 0.37, and I'm going to put a little red dot over here, right? Think about this blue thing not being here. So then you do another one. So you do another lower bound that has a different slope. So now we have a slope that's positive, and it's going to have an offset that's down here, something like minus 0.4. So I'm going to now be on the positive side, and I'm going to put my point here. Okay? And if I now do this at every possible point here, I put the tangents at every possible point for all the different slopes, which I plot here, and then all the different offsets here, then I'm going to carve out a second function over there. Okay? So you see this, right? So you take this one, gives me 1 point. This is the x-coordinate, is the slope, and the y-coordinate is the offset, and I put it here, I put the green one here, I put the black one here, so that's negative, so it's over here, and so on. And I'm going to, so this one, where is it? Here somewhere. And I'm going to get a second function, and that second function is convex as well, right? And that is something called Ventil duality. So I'm going to basically, from one convex function, I can generate a second convex function over here by basically representing the first convex function as its maximum of its lower bounds, right? And then, I don't know, anybody guesses what happens if I apply the same trick on this function over here? What do I get? Yeah, it would be a bit weird if I get a third one, because then, I mean, where should this go, right? Well, it could be, but I don't know. But in this case, you can easily show that you get back the original one. So it's a duality. I already gave it away by this word up here. So why is this important for our problem? Because if I can do this with a convex function, and I can even understand in terms of a second convex function what it is, I can use this, I can go back through this transformation, and I can apply this to lower bound my Gaussian function, my super-Gaussian function with all these Gaussians, right? I just go back through this transform, I apply the E, and I go back through this S square, and I plug it in here. So here I have my Gaussian, which would be the linear function here. That's the linear function. I go from that linear function, I plug in S square here, and I take E of that, and I get this one, right? So I do get the representation out of this Ventil duality, and I even get this function in closed form that I need in order to control the heights of these Gaussians. Okay? I think this, I mean, if you look at this for 5 more minutes, then it's being completely clear. I hope I explained this pretty okay here, but here's the picture for it. So you do want to represent this, let's say, Laplace potential as a maximum of Gaussian functions. So take one Gaussian function, has a certain width, which scales with its variance, or with the square root of its variance. So you got to fit it below the Laplace so that it just touches, right? If it was a little bit higher, it would go beyond the Laplace. If it was a little bit lower, it wouldn't touch it, right? So there's a certain height that you have to scale this Gaussian so that it touches the Laplace from below. And that height is given by that h function. And that h function you can get out of the Ventil duality if you want to do it that way. So you can now solve for this h function. You know what it is in closed form. You can work this out for all the potentials that you're interested in if they are super-Gaussian. And then you can represent that whatever potential you're interested in terms of all the Gaussians that fit it neatly from below. Okay? So that's just what it means to be super-Gaussian, and the Ventil duality gives you the mathematics in order to deal with it. So now how do I use this in order to get an approximation to the log partition function? In this case, I'm actually going to get a bound on the log partition function. Is anybody kind of has an idea how we could do that? Well, it's actually really quite simple. You look at the log partition function, right? So it has a Gaussian likelihood. And you say, okay, Gaussians are okay, I can integrate against Gaussian, don't have to do anything, but I have to do something about that prior. So I'm going to plug in, the prior is a product of potentials. I just know that every potential can be written as a maximum, so I can plug this in here. Okay? Yeah. Okay. So if I plug this in here, I can then, so I haven't done anything, but I can now interchange the integral and the maximum, and I get a lower bound. Okay. So I get a lower bound to the log partition function, and what is important now is that this integral is a tractable integral. So it's a Gaussian integral. There's nothing non-Gaussian here anymore, and so I can work out what that is, and I can then optimize over this gamma. Okay, and that's the variational problem. So you get a Gaussian approximation by basically by going this way. This is a log partition function of a Gaussian. You plug that in. You get this thing as the Gaussian approximation to the posterior. And you even get the problem that basically tells you how to adjust this parameter. You got to maximize that lower bound. And that is giving you the variational problem that you want to solve. Okay? And so that's the way how it goes. That's one of the simpler variational approximations. It's related to map estimation. If you just think about doing the same with map estimation, so you replace the prior as a maximum over the variational parameters, then you see that the map estimation is a maximum over the image. It's also a maximum over the variational parameters. And now you can do this in any order you want, right? You can change the order and you get equality here. So one particular way of solving the map problem would be that. For inference, it's a little bit more difficult. You can do this, but if you now interchange the both, because they're not the same anymore, you do have to suffer some slack here, and that's of course the approximation in approximate inference, right? But you can then still tighten the bound by maximizing outside. I think I'm going to skip over an algorithm that you can use in order to solve this at large scales, because interest of time. I think what I want to get at is a comparison between sparse estimation and sparse inference. So there's an algorithm that you can use in order to solve this problem at very large scales. And the important thing about this algorithm, I'm going to just skip forward. So the basic message here is that this algorithm is something that iterates over algorithms that we already have. So it's an iterative algorithm that iterates over map estimation in this case. So that's interesting because map estimation was iterating over these linear optimizations, right, in the first part of the course. And now we're going to iterate over map estimation in order to get inference going. It's not quite as simple because there's a second problem that you have to address for which you cannot use map estimation, but you have to go a little bit and dive elsewhere. But this is also doable. So in some sense, you can reduce inference to the estimation problems. So the message here would be that using inference, you can do more interesting things. You get a distribution instead of just a point. But again, you can reduce it to similar computational mathematics, right, that you already have. And I basically really only show you a single algorithm here, single relaxation. There are many others. This is a very active field. And there's also, this is used a lot for discrete inference, which I didn't talk a lot about. And then, of course, there's all sorts of randomized approximations as well, right? So I think the last point that I want to make here is that I want to compare estimation and inference with each other so that we get a little bit more insight in how they compare. And this part is not dependent on the algorithm, so I think I've skipped the right one. So let me just put up 3 questions that some of you might have. It's really been really confusing. First I said, oh, you don't get zeros. Then in map estimation you get zeros, and then in inference you don't get zeros, right? So what the hell is this guy talking about? When do I get these zeros, and why do I get them? Then you also have to admit that sparse inference is more expensive than sparse estimation. Why is that, right? And the third question is, what is actually the range of things I can do with sparse estimation versus what I can do with sparse inference? Can I, for example, optimize my acquisition by just running sparse estimation? Can I do Bayesian experimental design based on sparse estimation? Like, for example, you might have heard about the relevance vector machine or the ARD method. Can I base my decision making based on these methods? Yes or no, right? And how would I do it? So in order to address these questions, let's just look at another sparse estimator that's been very popular out there. It's not the map estimator. It's actually more fancy, and it's a better sparse estimator. It's called the automatic relevance determination estimator, or otherwise you can also call it a relevance vector machine, right? So Mike Tipping came up with that, and then David Wipf did some really amazing work in order to, improve our understanding of that method. It creates sparsity by basically having these gamma, pretty much the same variables as in the inference method, but it's trying to drive them to 0. Okay, it is an estimation method. It's not an inference method. You can actually get it as a limit of an inference method, and there are kind of quite a few algorithms in order to solve this problem at large scale. They are a little bit more difficult than the Lasso, but it's really worth it because this method gives you better results. So I want to now take this algorithm, which has this objective function, and I want to contrast it with the relaxation that we just had, which is actually doing sparse inference, and I want to see where the differences are, okay? So the first thing to note about these methods is that it's the gammas that matter. If the gammas go to 0, you're going to get sparsity. And in a very strong sense, if a gamma goes to 0, then I can show that under the posterior, the variable is completely eliminated. Okay, the corresponding variable is not there anymore. Its mean is 0 and its variance is 0. Okay, so it's completely switched off. The posterior puts 0 mass on that thing. So it's forced to be 0. It's put 0 mass on every other value than 0. So the gammas control exact sparsity. Okay, when they go to 0, it's switched off, otherwise they're not. And that is, of course, has the consequence that if I drive a lot of these guys to 0, right, then I will also kill all the covariance in that part of the space. It will be completely 0. There will be nothing left there. It will be forced to be 0, so there's no covariance anymore. There's no link with the other variables. This stuff is not there anymore, okay? It's like support vector machine, okay? They are gone, right? You can throw them away afterwards. And that has positive consequences, right? And these positive consequences are computational consequences, because if I do have a very sparse solution, I only do have to do heavy computations within the space that's not eliminated. Okay, so you can solve this at large scales. It also has bad consequences, and that is in particular if you're interested in Bayesian inference, uncertainty is eliminated. It's not gone anymore. And the interesting thing is, the less data you have, the more uncertainty is eliminated. Because the less data you have, the more sparsity the method can actually afford. So if you start with little data, like in a sequential experiment design, you start with a few measurements, you kill almost all of your space immediately in the very first iteration, and you never get out of that hole anymore. Okay? So sparsity, in that sense, is controlled by the gammas. It is good for computation because it eliminates coefficients. It's bad for inference because it eliminates coefficients. Okay? If you have no uncertainty in coefficients anymore, then you can't reason about them, right? You basically made your vote before you even started the whole thing. And here's the last picture that I want to show. And that shows you why the ARD method creates sparsity and the other one does not. And that's actually something that I hope that I can get this across, because it's a very beautiful fact. So these two are the different optimization problems. So this is the ARD, okay, and this is the variational inference that we've been talking about. They both look like Gaussian integrals. They are Gaussian integrals, and then you optimize over gamma, right? But now the crucial difference is that here the Gaussian prior is normalized. So it's a normalized distribution. So if you look at these Gaussians here, then this is a Gaussian and that is a Gaussian. So the more narrow this normalized Gaussian becomes, the higher it becomes here. So if I make it very narrow, it will just go off the roof. Okay? But the mass will always be the same, it will always be 1. So that means if I now optimize this thing over gamma, and it can afford to switch some of these gammas off, it's going to do it because it doesn't have to pay a price for them. And so it actually is even beneficial to turn them off. There's basically a drive for driving gammas to 0 because of the normalization. Okay? Because you're allowed to go through the roof here. Okay, the mass is not affected. So over here, it's a very different game. It's also a Gaussian function, but I have to stay below this Laplacian. Right? Remember, I need to be below that thing. I cannot go through the Laplacian. So if I want to go more and more narrow, what's going to happen to the mass of these potentials? They're going to converge to 0, right? So if I wanna switch anything off here, then I'm going to create at least one of these potentials is going to have a mass that goes to 0. So what happens to an integral if one of these potentials in mass goes to 0, the whole integral is going to go to 0. And if that integral goes to 0, then that whole criterion goes off to infinity, right? So what that means is that it's impossible under variational inference to switch off any of these gammas. It's not allowed. If you do that, you pay infinite price for it, right? Here it's encouraged to eliminate things. Here it's forbidden. And the reason is exactly because we don't want to kill coefficients in inference. We want to be uncertain about them. The only way how you can kill coefficients in Bayesian inference is if you have infinite data. And you don't have that. Right? So I think I want to stop here. So that was just what you could learn from this last part. This is a big field. There's lots of activity in variational inference, not just on sparse models. Of course, I've skipped a lot of things. I just want to point out a little bit of software that you can use in order to play with this. It's been done by Hannes, who also has been a student here. And I want to thank people I did some of this work with here. And yeah, I hope you enjoy the rest of the show.
Questions?
Yes.
So I have two questions regarding the variational base. First one, what if the potential is non-super-gaussian? Are you still using Gaussian to approximate that?
So there are other variational approximations. So you could not use the one that I've been showing you here because that only works for super-gaussians. You need that initial thing. But there are other more general variational methods like expectation propagation that you can use in this case. And Tom Minka is here, so you can ask him. He knows more about it than me. But so this is a more general method that can deal with more potentials. It can, for example, deal with non-negativity. And you could run that. It would be computationally a bit more difficult if you applied expectation propagation to things like that. I just wanted to show you a simple one. But don't think about variational inference as only being that one. It was just an example.
Okay.
Yeah.
So the second one is if the best Gaussian you choose that approximate the super-Gaussian potential, is there any connection with the one that maximize or minimize the KL divergence?
Yeah, there is a connection with KL divergence, which I could have just put up. It's basically a very direct relationship to KL divergence. Although you've got to really always look at the details, because for some variational methods, there's not a direct relationship to the KL divergence. But for this one, there is one. You're right, it's a KL divergence that's being minimized here.
Any more questions from the observation lounge? Anybody?
Yes, we have a question.
Very good.
Oh, wow. First time.
Hello. So I have two questions. So at the beginning of your talk, you showed the example of the images, and so basically it can be represented by two representation, right? So my question is, in practice, how do you decide whether sparse representation is the right representation that we should use? And so the second question is that when you consider integration over the posterior distribution instead of the map estimate, does it still make sense to discuss about sparsity? Because you could imagine that the non-sparse solution could also inference the solution.
Okay, so
thank you.
First question was about which, if I understood it, which sparsity potential to choose. I mean, the first answer is don't use Gaussians, use anything that gives you sparsity. It will always work better if you can do the algorithmic problem. Among the different sparsity potentials, which one should you choose? Well, there are two things you have to keep in mind. One of them is if you choose the Laplace, you're going to have computationally a much easier game. So many people will go for the Laplace. We went for the Laplace. If you choose other things, you might get statistically better answers. So you have to compare these things. And the best thing you can do is to have software that can deal with different potentials and then just play with it. So, for example, this software can deal with a range of potentials, which also includes the student T and so on, right? But you got to really understand that these variational methods, they are not uniformly good approximations to the posterior. They might depend on the choice of the potential might also determine how accurate your approximation is. And that is an additional thing that complicates that choice. But so in general, I would always go for the best model for my data and then think about the approximation, right? And the second question is, so what does it mean to use variational inference with a sparsity potential that doesn't really put mass on zero? I think that really depends on what you want to do. If you want to reconstruct an image, it's actually not that you want to create zeros, right? It's just not, that's what some people tell you, but it's not true. You want to create a prior distribution that fits your signal better than other ones, and the sparse distributions are actually pretty good. If you plot image statistics, they are not sparse, right? And unless you take, I mean, you can take cartoon images, then you get zeros. But if you do plot anything out there in the real world, you never get zeros. And so I think you should probably not use priors that do put mass on zero. Now, if you have a problem that you want to put mass on zero, you can do this. It's called spike and slab. I didn't talk much about it, but there are Bayesian methods that do put mass on zero, right? It wouldn't work quite as easy as what I've shown you here. But for example, expectation propagation is a method that can deal with priors that put mass on zero, but it's more difficult. Okay, I hope that answers the question a little bit. Otherwise, I'm around also here, also Monday, and I'm really happy to take more questions.
Any more question right now? I have one more question. So, to solve these to calculate these difficult integrals by variational approach, you solve it by an optimization problem, right? Or you also said you could use MCMC. Basically, both are for loops, right? Complicated for loops. So now you said something about that there are some pros and cons in your work. So yeah. What would be the pros and cons of variational versus MCMC?
So it all comes down to it really all comes down to, so MCMC is clearly a technology that if you have enough time can be more accurate and does give you better results than variational almost in general. But if you are working under constraints, so think about the experiment design problem, right? You have sequential experiment design, you do have to make decisions, you have to make repeated decisions, you do have to make a decision. Now I've done this many measurements, what's the posterior? Now I've done one more measurement, what's the new posterior? This is something that is very, very hard to see how you could do this with stochastic optimization, because every time you pick a new measurement, your samples are basically useless. You have to sample again. You're going to have, even discounting the fact that sampling from such a model is actually really quite difficult. You have to spend a lot of time even to get one posterior sample for a fixed set of measurements. But if you change your measurements in any way by saying acquiring a little bit more of that image, you've got to do all that work again. Right? And you got to have the stochastic noise in there, and it's just difficult. So I am somebody who really admires MCMC. It's great piece of technology, and if you want to be absolutely sure that you get the best possible answer for your problem, I think you should go for MCMC, right? But if you're working under technical constraints that tell you, okay, you got to give an answer in this amount of time, and you got to give an answer about which you can say something like, hey, it's a convex problem, it's a robust problem, it's a problem that has some smoothity properties as you walk through the space of measurements, for example, then you might be better off with variational methods, right? MCMC is also something that is more like a black box technique, but I'm not so sure, because in the end you gotta be really careful how you use these samplers. They look simple to run, but in the end, they don't have a notion of convergence, so it's a little bit difficult to see when they're actually done and when you just start to waste your time. It's really something that you should know about both and then pick and choose. But for sequential experiment design, I think we probably are better off using a variation.